Oops, there we go. All right, so let's take a look at that problem I gave you guys end of last class, and we'll see, there we go, if we can sort it out. Get myself to. Oh, yeah, sometimes that happens, Merrick. Sorry about that. So you should hopefully be able to catch up a little bit over the weekend if you're not working too much then. And maybe then you'll have more questions on Monday for me. And then you can get together with Aaron E for an adult beverage. Okay, anyway. So Sunday's your big homework day then? Sunday used to be always my big grading day too. Yeah, bummer. Okay, so it makes the weekend end a little bit too soon. Let's take a look at that problem that I asked you guys to do. It was this one. So integral, you guys said it was cosine. So it was e to the x cosine x dx. And the way integration by parts works, remember, is that we're going to choose everything in our integral. We don't get to leave anything out. And everything is going to be made up of u and dv. And then we differentiate to find du, and we integrate to find v. And then we use our integration by parts formula. And keep in mind, our integration by parts formula was integral of u dv equals u times v minus integral v du. And we're going to use this a little bit today to come up with some things related to trig functions. So keep this in mind as we move forward. So we kind of have two choices here. And if we use that sort of rule of thumb little mnemonic phrase that I gave you, that liate, if we use that on this, as we move from left to right, trig functions come first for choice of u. So I'm going to go ahead and go with that. I'm going to let u equal cosine x and let dv equal everything else, so e to the x dx. In this problem, it actually wouldn't matter. I could just as easily have let u equal e to the x and dv equal cosine x dx. So this is one of those cases where you're going to get to the right result no matter which one you chose. So that's kind of nice. All right, so we've got our u, we've got our dv. We're going to differentiate to find du, negative sine x dx. And we're going to integrate to find v. V is e to the x, since integral of e to the x dx is e to the x. All right, now we've got all of our pieces. Integral of e to the x cosine x dx is u times v, so cosine x times e to the x minus integral of v du, e to the x times negative sine x dx. So really the most problematic thing here is that nothing much changed. This new integral looks an awful lot like the original one. All I've really done is translate a cosine into a sine. So are we good so far on that? Give me a yay in the chat or a something. A couple of ups in there. All right. So we're going to have to use integration by parts again. And when we do this, sort of a nice thing to remember is whatever you did to start with, don't change tactics in the middle of the game. So you've sort of picked a battle plan, And your battle plan was to let u equal the trig function. We're not going to trade off. We're going to keep u equal to the trig function. So let's see what happens. I'm just going to put my equal sign here. I've got, oops, not an e. And actually, I'm going to translate those or transpose those. E to the x cosine x, and then plus integral of e to the x sine x. So again, we're going to let u equal the trig function. dv is the exponential. V is e to the x. And kind of nicely this time, du is cosine x dx. So I don't even have any negative signs to deal with on this. All right, let's put everything together again. E to the x cosine x. So we're just repeating. Plus u times v, e to the x sine x, minus integral of v du, e to the x cosine x dx. And remember, what we were calculating in the first place was integral e to the x cosine x dx. Okay, so what happened? I have this integral I'm trying to compute on the left, and I came up with, take a peek here, I came up with this other integral, which is the same thing that I was trying to compute. Do you guys see that? See how my new integral is exactly what I started with? Which means there's no need to keep trying integration by parts, because anything I do further is just going to circle me back through over and over again. And you could think, okay, well then this really led us to a dead end, but if we look at it closely, it didn't. And here's why. So the integral on the left is what we're trying to compute, and the one on the right is the same thing, but the key is, and this is really nice and important, there's a minus sign in front of it. So let's call that integral, I don't know, you know, mathematicians love variable names or something. Let's call it I for integral. The integral is equal to e to the x cosine x plus e to the x sine x minus the integral. How could we figure out what the integral is equal to? In other words, how could we solve for I? What's going to happen there? Yeah, add it to both sides. So 2 times the integral is e to the x cosine x plus e to the x sine x. And that means the integral we were trying to figure out, right to the bottom of the page, is 1/2 of e to the x cosine x plus e to the x sine x. And I'll put my plus c in now because I've been neglecting it. There it is. So this is one of these problems where we end up with the integral, the original integral in the problem using integration by parts, and then we're able to solve for that unknown integral. Yeah. So these kinds of pop up. It is kind of wild and sort of fun. I'll show you another one that's going to actually lead us to some really neat formulas for trig functions. I know formulas and neat probably don't go together, and neat is a really old time word, showing my age here. So, but we can use integration by parts to sort of develop some interesting little what we call reduction formulas for trig functions, and so those will come into play today. Okay, did you guys try any other of those problems on that worksheet from last time? I need to find it again, since I can't open it in the, I can't seem to open it in the Zoom thing. So I'm gonna go look for that. That was, that one. Oh. Okay, so I'm just looking back at that worksheet that we had from last time with those practice problems on it, and I think we did 1, 2, 3, 5, maybe. I think we did 6. We did not do 7, and 7 was a definite integral. So let's go ahead and try this one. I'm going to have you guys, I'll go ahead and write it on the, let's see, new page. I'll go ahead and write it on the whiteboard, so if you don't have the document open, that's okay. It was integral x cubed ln x dx. And this one's a definite integral from 1 to 3, so we're going to have to evaluate. Oops, not 1 to 3, 1 to e. There we go. So we're going to have to evaluate this one when we get done. So let's go ahead, give this one a try. And there's, let's see, and then we'll do a couple more. Okay. So we'll pull some problems from there, and then we're going to look at this idea of trig integrals and see what we can get from it. Okay, so what do you guys think? What should I let u equal on this problem? Remember our fun little, yeah, ln x. ln is all the way over on the left-hand side. It's our best choice for u because we don't have a formula for integrating ln x. So we're going to let u equal ln x, and then dv gets to be everything else. dv gets to be x cubed dx. Now, you might have looked at this and thought tabular integration, but remember, for tabular integration, we need 2 things to happen. We need u to be a polynomial function, which I suppose we could do. We could have done the x cubed, but then we want dv to be something easy to integrate, and ln x requires integration by parts. You really don't want to use an integration by parts problem on that very first step. You want dv to be something that at worst you could integrate by a substitution. So we're going to let u equal ln x. This is a nice thing because when we compute du, the natural log is gone, 1 over x dx. Now when we compute v, we do go up in powers, so that's a little bit messy looking, but it's not horrible. X to the 4th over 4. We should be able to deal with that since it's a polynomial. So let's put all of our pieces together. uv minus integral v du. And this time we're going to have to make sure that we write everything out in terms of evaluating. So u times v is x to the 4th times ln x over 4. And we're going to evaluate that from 1 to e. Minus the integral of v times du, x to the 4th over 4 times 1 over x dx, also from 1 to e. All right, so what should I do with that? So the first part of this is something we're going to evaluate. So we're all set there. We're done integrating. The second piece is an integral of a product. Can I do anything to make that nicer looking? What could I do with that? Cancel x from top and bottom. Good, Aaron C. So this x can cancel with one of these guys. Oh, so that's just a power of x, right? That is just minus, oops, let's switch back to black, minus the integral from 1 to e of 1/4 x cubed, or minus x to the 4th over 16, because we get 2 4s in the denominator. And then our first term was x to the fourth ln x over 4. And now all of this gets evaluated from 1 to e, and we're ready to plug in those limits. So let's plug in the e first. E to the fourth times ln e over 4 minus e to the fourth over 16. And then plug in 1 to the fourth ln 1 over 4 minus 1 to the fourth over 16. So this looks a little bit ugly, but I think we can sort a couple things out. Remember, natural log of e is 1, so that's going to be nice. And natural log of 1 is 0. So I've got e to the fourth over 4 minus e to the fourth over 16 plus 1/16. And if I get a common denominator, 4e to the fourth over 16 minus e to the fourth over 16 plus 1/16. So if they do want an exact value on this, it would be 3e to the fourth plus 1 all over 16. So it looked like maybe we were going to have to use integration by parts more than once, but it was really only required one time. Yeah, sometimes that happens. All right, I'm going to have you guys try one. This one's a little bit different. So this is one from that worksheet too. And again, so you guys don't have to go back and drag it out, I'll just add it to the, oops, I'm going to go plus a page. Let's try this one. Integral sine inverse x dx. So this one's not a definite integral, just an indefinite integral. You're going to use integration by parts. See if you can figure out what to let u equal, what to let dv equal, and then go from there. And I'm going to pause the recording while you guys think about this for a little bit. Unpause the recording. All right, tell me what to do next. You can tell me in chat or you can tell me out loud. How do I finish this up with that last integral? Did you need a specific technique or did you just know the answer?
I use u substitution to figure out the
Okay,
integral.
good, Caitlin. What did you let u equal?
1 minus x squared.
Sounds good. That's what I would have done. Okay, good, Aaron. Aaron says same. And it's going to turn out as we move through this chapter and we see more techniques of integration. There are some other techniques that you could use for this integral. However, substitution will still turn out to be probably the most straightforward. So du is negative 2x dx. And dx is du over negative 2x. So I'm going to put all my pieces together. X over square root of u du over negative 2x. And I'm going to factor out that 1/2. Oops, not an equal sign. Let's fix that. Minus plus. My x's cancel. And I've got u to the minus 1/2. Du. Is that what you had, Caitlin?
Yep.
And so we're ready to integrate that, increase the power by 1, divide by 1/2, which is the same as multiplying by 2, plus c, and let's not forget our x sine inverse x from the first term. So we're almost done. We just need to clean this up a little bit. We can cancel those 2's, and u to the 1/2 is the square root of u. So x sine inverse x plus the square root of u, or square root 1 minus x squared plus c. And you can go through and take the derivative of that thing, and you will get the inverse sine function, strangely enough. So the square root of 1 minus x squared will end up canceling with one of the terms from the product rule in the first term when you take the derivative. So not too bad. And really, this is maybe about as messy as these should get. I mean, you might have to use integration by parts more than one time, but in terms of your integral for that second piece, like this integral, the worst you should have there is something you can do by a u substitution. So keep that u substitution in mind in your back pocket. All right, we are going to try, let's see, there were a couple more on there that I wanted to look at, so I'm going to go back and take a peek. If you guys looked through the rest of that worksheet, you probably saw some powers of trig functions in there. And we're actually going to go to one of those, but we're going to do something slightly, oh, I might have it in there as, yeah, number 15. We're going to do that one using integration by parts, and that's going to kind of lead us to some other ideas for trig functions. So let's take a new page, and number 15 on that sheet was integral of cosine cubed x dx. And we're going to look at this two different ways and come up with what will appear to be two different answers, and then we'll sort of look at those and make sure that they're actually the same thing. So if I'm thinking integration by parts, I need to let u equal something and let dv equal something. Well, I have formulas for derivatives or for integrals of trig functions, but I don't have nice formulas yet for integrals of powers of trig functions. Unless this were, say, a secant squared, then I would be okay. Since this is a cosine and it's cubed, I'm going to go ahead and I'm going to think, you know what? I know the integral of cosine x. So I'm going to take my cosine function, just one factor, and put it over here in dv. And yeah, I'm allowed to do that. And the reason I'm allowed to do that is that there's no glue holding those three factors of cosine together. They are truly three factors of cosine. And so I can split them up however I choose. How many does that leave me for u? If I used one of them over here in dv, that leaves me two more here. So that's kind of interesting. And you could kind of think, if I had 10 factors of cosine there, I could push one over to dv, and I could leave 9 of them in u. I could always just take that one away and then have the rest of them left for u. This is very nice. V is sine x. Integral of cosine is sine. My du is maybe not so nice because I need my power rule. 2 times the cosine of x times the derivative of cosine x, which is negative sine x. So it's a little messy. But I've got my u, I've got my du, and I should be good to go. So let's write in all the pieces. U times v, so u times v, cosine squared x times sine x, minus the integral of v times du, sine x times negative 2 cosine x sine x dx. And that's a little bit ugly, but it's doable. Plus 2 times the integral sine squared x cosine x dx. Does that make sense so far? Again, notice that they can get kind of long, but they're not really undoable. A couple things to point out. Notice that the power on cosine in that first term is cosine squared, so it's one less than what we started with. And that's because we split off one of the cosines. The other factor there is a sine, and that's because sine is the integral of cosine. So that's kind of something that would happen no matter what that original power was. Also notice in my new integral, the power on cosine is 2 less than I had before. Not 1 less, but 2 less. Because I took that cosine squared, I differentiated, and when I differentiated, I went down 1 more power. So that power is 2 less, and then we've got that extra factor of sine squared. The nice thing here is that we can now do this by substitution. We could say, okay, let's go ahead and let u equal sine x. du is cosine x dx. And this looks like plus 2 times the integral u squared du, or plus 2u cubed over 3. And then not forgetting my first term, cosine squared x sine x. And finally, write everything in terms of x, cosine squared x sine x plus 2 not cosine, undo, sine cubed x over 3. So that is one correct answer to that problem. That's one way to do it. Notice that this method would have worked even if we had started out with, say, a cosine to the 6th power. But what would have been problematic is that this new integral would have had more factors of cosine hanging around in it. In fact, it would have been a cosine to the 4th power. But these factors of sine would have still been here. So we're going to take a look at how we could sort of make that into a formula. Let's try this one other way. So I want you guys to go back to trigonometry. So think back to your trig class and think about how or what identities connected sine and cosine. Can you think of an identity that connected only sine and cosine, no other functions? So I don't want you to use tangent. Just think of an identity that connects the sine function and the cosine function. And this is where you get to think for a minute, well, why would I want to put a sine in here? But you'll see in just a minute. So who remembers an identity that connects sine and cosine? You can look for one in the chat. Sine and cosine. Think unit circle. What was the identity that related to the unit circle? No, Merrick, it doesn't. 1 over the sine is the cosecant, not the cosine. I think that's the one you're thinking of. Yeah, sine over cosine is tangent, Aaron, but I want you to give me an identity that doesn't use another trig function. So just sine and cosine. And think about the unit circle. That's okay. What did the equation of the unit circle look like? The cosine is the x value and the sine is the y value. And the equation of the unit circle was x squared, I'm just going to jot it over here, x squared plus y squared equals 1. And the cosine was, chat is driving me crazy. Get that out of there. The cosine of the angle is the x value, and the sine of the angle is the y value. So we can use that no matter what our variable is. And we have this identity that says cosine squared x plus sine squared x equals 1. And the reason that this identity is useful is really the same thing we just did in the last problem, but we're going to do it thinking substitution instead of thinking integration by parts. So I'm going to split this up. I'm still going to take a cosine squared, and I'm going to take a cosine x. Then I'm going to split them apart, but then I'm going to use the fact that this cosine squared x can be thought of as 1 minus sine squared x. And if this problem involved sine, a power of sine instead of a power of cosine, I could let sine squared x equal 1 minus cosine squared x. So I'm going to just make that substitution in here with my identity, 1 minus sine squared x. And then I've got a cosine hanging out here, which is nice because remember, cosine is the derivative of sine. So we're now set up nicely to use a substitution. What substitution will work on this problem now? What u could I use for a substitution? Let's see, the derivative of sine is cosine, and I've got that sitting right here. So I would like that to be my du, and that will happen if I let u equal sine of x. And du is cosine x dx. And that means my integral now takes this very nice form, 1 minus u squared du. And we've eliminated all trig functions. We're just integrating a polynomial now, u minus u cubed over 3 plus c, or u is sine x minus sine cubed x over 3 plus c. Okay. So that, at least for this problem, seemed like a little bit simpler way to go. And it's going to kind of depend on your problems. So the method we used with integration by parts last time was maybe a little bit longer, but I'm going to show you some formulas that come out of that integration by parts that can make that work a little bit easier. So does that make sense? All right. I am going to share a document. Merrick, I'm going to put a document in the chat. I know you have trouble getting those, but I did already upload it to e-learning, so you can grab it there as well. So this one is evaluating. Okay, so hopefully you guys can see my screen. It looks like you can. This is the one I want. Okay, so what this section is about different ways to evaluate trig functions. So the first 6 formulas on this sheet are what I'm calling the basic formulas. The top 2, I know you know. You've seen those before. Who has seen these formulas for tangent and cotangent before? Who remembers those? Not that I can recall, says Merrick. And you may not have, especially if you had Calc 1 in our shortened, messed up winter semester. So we're going to look at where a couple of those come from. If we can get the formulas for tangent and secant, you can kind of see how the formulas for cotangent and cosecant would be developed in a similar way. So we'll start there, and then we'll look at these other formulas as we move down. So I'm going to go ahead and stop that share, and we'll share from here again. All right, so let's take a look at that next one, which was integral of tangent. You guys said that you didn't remember that one. Okay, so on this one, we do want to remember that, and you guys gave me this formula a few minutes ago, that tangent of x is sine x over cosine x. So we're going to go ahead with that substitution, and or that replacement. And then we're going to try a substitution. So tell me what substitution I might use at this point in time to finish up this integral. What could I let u equal? Well, if I look back at that formula sheet that I just shared with you guys, yeah, I could, Merrick. I'm going to play devil's advocate and do what Merrick said. This isn't right, by the way, but we're going to see what happens. If I let u equal the numerator, sine x, du is cosine x dx. So dx is du over cosine x. And if I take this route, I've got integral of u over cosine x times du over cosine x. Now, I'm not saying that I can't do this, but notice that I now have this thing down here, this cosine squared x, and that's not my u. My u was a sine. Now, I suppose I could write that as 1 minus sine squared x, and I could then call it 1 minus u squared and do a substitution. So it is doable, but it's going to be messy. Alternately, so we're going to kind of X through these guys. They weren't wrong. It's just not looking as clean as I would like. Alternately, I could let u equal cosine x, my denominator, and du would be negative sine x dx. Now, the negative sign might seem a little bit more messy, but now my dx is du over negative sine x. And when I plug that in, integral sine x over u du over negative sine x. I've got 1 sine in the numerator, 1 in the denominator, and those guys cancel. So this is really kind of nice. I've got negative 1 times the integral 1 over u du. So if you do have a fraction and you notice that the numerator and denominator are derivatives of each other or close to that, you're almost always better off letting u equal the denominator so that your du can cancel with what's in the numerator. And then integral 1 over u was natural log of u. So minus natural log of u plus c, or minus ln cosine x plus c. And if I go back and share from the other place, let's see that one. That is that first formula. Integral of tangent x is minus ln cosine x. It's possible to write that in terms of ln secant x. Remember, coefficients in front of trig functions can come up as powers, and the reciprocal of cosine x is secant x. So that's where that comes into play. Similarly, for cotangent, you would just let cotangent be cosine over sine, and you should be able to develop that formula for ln, for integral of cotangent. All right, let's peek back. I'm going to stop my share. Double check that chat. And let's try another one of those. Whiteboard. Let's try integral of secant x dx. And this is one that we almost never get to in Calc 1, no matter how the semester goes. So this one requires a tiny bit of a trick, and we're going to actually use the answer as part of our trick. So the answer has a secant plus a tangent in it, and it turns out that if we do a clever thing and multiply by 1 in the form secant x plus tangent x, and the question is, how would you think of that? Well, somebody did, so we don't have to. So take a peek at that. Does that step, even though, you know, it's one of those things I would never think to multiply by secant x plus tangent x on my own, maybe, but does it at least you realize that that's a doable thing? All I did was multiply by the number 1. Now let's take a peek. We're going to simplify the numerator, secant squared x. Now wait a minute, secant squared x is the derivative of what function? Somebody shout it out loud. Secant squared x is the derivative of, I know somebody knows. Derivative of what is secant squared x? Plus secant x times tangent x. Yes, plain tangent x, Merrick, no minus sign. I don't know if that's a minus sign or a dash. Derivative of tangent x is secant squared x. Now my second term in my numerator is secant x times tangent x, and that's the derivative of secant x. So the numerator is the derivative of the denominator. If u equals secant x plus tangent x, du is secant x tangent x plus secant squared x dx. So du is all the stuff in the numerator, and u is all the stuff in the denominator, and the form of this integral is 1 over u du. So the integral is ln absolute value of u plus c, which is ln absolute value secant x plus tangent x plus c. So there's the function whose derivative is secant x. And similarly for, go ahead and switch my share again. Similarly for cosecant, the trick is going to be to multiply by a cosecant plus a cotangent. And then this all kind of comes together in a similar way, but with a minus sign. So integral of cosecant x is minus ln cosecant x plus cotangent x, or you can rewrite it like it is on the right. So it's up to you there. So those basic formulas are kind of nice. Remember, your test is going to be a take-home test, so you obviously don't have to memorize these. You should have the top two memorized already anyway. And there are going to be lots of formulas on this sheet. If I were giving a test, say in the testing center or in class on campus, I would give you this sheet anyway. So this really isn't any different than what I would do if we were doing regular class on campus. Let's take a peek at this next group of formulas. So this says I can integrate using trig identities. We actually did one of these already, an odd power of sine or cosine. So if you have a product that involves sines and cosines, and either of these powers is odd, this says, you know what, you can evaluate this integral by splitting off a factor of cosine or sine, depending on which one is odd. If they're both odd, you get to take your pick. With the even powers, if we want to use trig identities, since we don't have an extra leftover power when we split things off, we're going to use these double angle formulas or half angle formulas in this form in order to do some rewriting. So we'll take a look at some of those as well. The other option, I'm just going to sort of show you the last page of this, is what we call reduction formulas. So these reduction formulas are actually what comes out of using integration by parts and allows us to go from an integral of a power of sine or any trig function to an integral involving two lower power, so two less than what I started with. Same for all of them. Notice that in the new integral, you have a power that's two less than original. So we'll take a peek at some of those as well. If our problem involves tangents and secants, we're going to use this identity, secant squared x plus tangent squared, or equals tangent squared x plus 1. Using that identity, we can rewrite. Or we might use it in a slightly different form, tangent squared x equals secant squared x minus 1. So we'll look at scenarios for each of those along the way. So I'm going to stop that share. Again, you might want to keep that handy. You might even want to print that one out if you have a printer. If you don't, maybe just take the PDF file and put it on your desktop somewhere where you can get to it and look at it pretty easily, because it's a nice handout that has all of those formulas in one place. Okay. Sure, Merrick, I can. I have to just share from back on my iPad. And that was, let's see. Where did it go? Okay. I'm sorry, Merrick. You should be able to go back and watch back, because it did get recorded. But I don't know what happened to it. All of my problems that I did so far today are gone. I just have two blank whiteboards for some reason. Okay, sorry about that. We're probably going to do something similar to one of those again anyway, although I do want to jump into some that use um, the identities and or the reduction formulas. So let's actually take a peek at one of those from the worksheet. Oops, not that one. Let's see, not that one, this one. Actually, no. Let's do this. I'm going to keep this a little bit smaller. Let's try integral of just a sine squared x. So this isn't too messy. So on this problem, what we want to notice is that the power on the trig function is even. So I'm looking at an even power of sine. And I'm going to use that half angle formula from back in trigonometry. Again, you don't have to have these memorized, but you have to know where to find them. So that sheet is really nice because it's got all of them in it. And the formula says sine squared x is 1 minus the cosine of 2x over 2. So this is really just the double angle formula for cosine rearranged so that we solved for sine squared x. What it allows us to do is allows us to replace a larger power of sine with a smaller power of cosine. And most notably, it's taking every sine squared and replacing it with a cosine to the first power, which we already know how to integrate. So that's sort of the idea here. We're going to take this, we're going to say, okay, that's 1 minus the cosine of the double angle, 2 times x over 2. And the 2 in the bottom is a constant, so I can factor it out. 1/2 integral 1 minus cosine 2x. And then I can integrate term by term. So integral of 1 is x. And then being careful with the fact that the coefficient of on x is 2 minus the sine of 2x divided by 2 plus c. So a quick little note, which this is just a little side note. If you have integral of cosine of a constant times x, that's going to be the sine of the constant times x divided by the constant. As long as a is a constant, that will work. And you can do the same thing with any of those trig integrals. So similarly for the sine function, integral of sine ax dx would be negative cosine ax over a plus c. If you had a secant squared ax, that a ends up in the denominator. And so we are all set. Now, one thing that's different about how this answer looks compared to if we did this problem with the reduction formula is that this is written in terms of the double angle, in terms of sine 2x. Notice we could go now and use our double angle formula for sine. 2 sine x cosine x over 2 plus c. And then we could cancel the 2's there. So 1/2 x minus sine x cosine x plus c. So that is that problem using trig identities. We can also do that problem with a reduction formula. So again, one of the problems in Calc 2 is that there are at least 3 ways to do almost every problem that you come upon. So I can't say you have to do a problem a certain way. Well, I could, but there are often many, many options. Where did I get the sine 2x over 2 from? Okay, that's this little integration step right there to there. So remember, integral of cosine is sine, but on that step, if you let u equal 2x, your du is going to be 2 dx. So dx will be du over 2, and you'll get that factor of 1/2. And that's actually connected to what I wrote over here with these sort of more generalized formulas for integrals of sine and cosine. If you have a constant times your argument, that constant's going to land in the denominator. Does that make sense now, Merrick? Yeah, and I didn't write out the substitution though, right? I just did it kind of in my head because I knew it was only going to be that constant factor. So that was a very fair question. All right, we're going to try that problem again. As I said, we can do most of these problems in at least 2 different ways. And this time we're going to use one of those reduction formulas that you see on that sheet. So keep this answer in mind. We're going to compare in just a minute. And we're going to go over here. I'm going to switch the screen share. I'm not sure why this thing is not saving, but hopefully that will be in there. Yes, I want to continue. And here we go. So I am going to simply come down here and scroll to the second page and these reduction formulas. So these reduction formulas allow you to take a power of a single trig function and reduce it by 2. So if you're at sine squared, you're going to get down to sine to the 0 power, or just the number 1. If you're at sine to the 5th, you're going to get down to sine cubed, and so on. And the problem we just did was, remind me, actually let me, I'm going to stop my share again so I can go back over here and share. Yeah, this is really weird. They don't stay. That's an odd new lesson for me to learn today. So you guys have that last answer written, I think, or hopefully we can go back and find the whiteboards. We were looking at integral of sine squared x. So what I'm going to do is I'm going to go to that formula sheet and I'm just going to write down the formula. The formula says the integral of any power of x. The only thing that's required about n is that it needs to be a whole number. So actually we could even say it needs to be 2 or more. So for n greater than or equal to 2, these formulas make sense. Otherwise, we end up with negative powers. We also don't want n to be a fraction. Things could get very messy in a hurry. So the integral of a power of sine is negative 1 less power, that was that 1 we factored out, times a cosine, oops, I need my x in there, divided by n, and then plus, no, not n plus 1, n minus 1 over n times the integral of sine to the n minus 2 x. So this looks really messy, but it's not as bad as it seems. We just have to get everything plugged in. I found that a lot of students actually like these formulas once they get some practice with them. So let's see how this works. Our n value is 2. So everywhere we see an n, we're going to plug in n equals 2. 2 minus 1 is 1. So minus sine to the first power of x times cosine x over n over 2. Plus 2 minus 1 over 2, 1/2, the integral of sine to the n minus 2, sine to the 0 power of x. So take a minute and peek at that and make sure that you can figure out where all of those pieces came from. So plugging in n equals 2 on the left and right hand side of that formula should lead to that. Now tell me what we have for sine to the 0 power of x. What is anything raised to the 0 power other than 0? 1. So that's just the integral of 1. 1/2 integral of 1 dx. And the integral of 1, or a constant, is the constant times x. So this is minus sine x cosine x over 2 plus 1/2 x plus c. And I think that matches up our answer that we had to the last problem exactly. In the last problem, you would have had to distribute the 1/2 in order to get it written in this form. But other than that, they are identical. You just needed to distribute that 1/2 after we used that double angle formula to rewrite that one. So most of these problems you can do, or at least many of them, by either using the reduction formulas or the trig identities, and it's going to probably come down to what your personal preference is. One thing to remember is that if your trig functions are mixed up, you won't be able to use the reduction formulas. Reduction formulas will only work if you have a single trig function. So for example, you could have a tangent to the 5th power of x, but you can't have it multiplied by something else. It's just going to need to be the tangent only and not the tangent multiplied by a secant or a cosine or some other thing. So be a little bit careful there, but otherwise you can use both of those methods. All right, let's try another one, and this one is from that worksheet. I'm not going to leave the that form again. This is from the worksheet, and it is, oh no, I want to go a little simpler than that, so we're not going to do that one yet. I lied. We're going to do a secant problem. So we're going to add page, and let's do a quick reminder. Integral of secant squared x dx is what? We just had this one on our basic formula sheet, tangent x. So secants and tangents are connected by derivatives. They're also connected with identities. So here's the one I want us to try. We're going to up that a little bit. We're going to integrate secant to the 4th power of x. And we are not going to use the reduction formula, although we could. We're going to use trig identities. And here's the way we're going to think about it. We know the derivative of tangent is secant squared. So I'm going to split off a secant squared. In other words, I'm going to think of this as secant squared times secant squared. Everything you ever learned about identities in trigonometry you learned for this class. Maybe not everything, but a lot of it. So if you don't remember those things, it's okay because you can look them up, but you're going to want to remember them more and more and more as you practice so that you don't have to look them up every time. Now, why do we want to do that? Because we can now use our identity that says secant squared x is tangent squared x plus 1. Secant squared x is tangent squared x plus 1. And now we're set up to make a substitution. We're going to let u equal tangent x. Du is secant squared x dx. So all of this was a plot, an evil plot if you like, so that sitting right here we have du, and sitting right here we have u squared plus 1. And then I can integrate u cubed over 3 plus c is tangent cubed x over 3 plus, plus u, I missed my second term, plus tangent x plus c. I forgot to integrate my 1. Integral of 1 is u, and u is tangent x. So these can get long, and they can get a little bit messy, but we've got sort of a plan. And the plan goes back to that worksheet. I'm not going to share on my computer again because every time I've done that today, I've lost my problems from the whiteboard. So that plan looks like, okay, if I've got odd powers of sine and cosine, I'm going to split off one factor of either a cosine or a sine. If I've got even powers, I'm going to use those half angle formulas. If I've just got a large power of one function, I'm going to try to use a reduction formula maybe. If I've got products of tangents and secants, I'm going to split off a secant squared and then use that identity for the rest of it. If I've got, depending on the powers, I might split off a factor of secant times tangent and use the identity in the reverse direction. So this can get kind of funky depending on which thing you're working on. If m is even, so an even number of tangents, and n is odd, an odd number of secants, I'm going to use an identity and then end up using just a reduction formula anyway. So this can kind of get messy, but we have a plan that will let us sort of go through any combinations of powers of trig functions. You'll notice in here, we didn't throw in cotangents and cosecants. We could, theoretically. They work very much like the tangents and secants, and we won't look at those separately. So you're not responsible for them. They're not going to pop up on a quiz or a test or anything. So any questions on those so far? I know there's a lot in there today. I think we're going to try one more problem. And no, what's back there? That's weird. So I'm just going to add a new problem. Let's try integral of, and we'll do kind of a mixed up problem. Let's put some tangents and some secants together. I'm going to go with a tangent cubed x times a secant cubed x dx. So I've got an odd power of tangent and an odd power of secant. And when I go back and look at my sheet, it says if M is odd. M is the power on tangent. It says split off a factor of secant times tangent. So let's just see how that works. You guys might not be looking at that sheet right now, but we're going to start by splitting off a factor of secant x times tangent x. Now, that might seem kind of strange, but remember that's the derivative of secant x. So we're thinking ahead. In the end of this, I want to write everything else in terms of secants and do a substitution. So let's see if we can do that. So I'm going to take away one of these tangents. That leaves me tangent squared. And one of these secants leaves me with secant squared. And then I've got secant x tangent x dx. And so I'm thinking ahead, this thing, I want this thing to be my du. That's my differential. And the only way that that can happen is if u equals secant x. Du would be secant x tangent x dx. So in order to do this, I need to take this tangent and write it in terms of secant. But I can do that because I know that tangent squared x is secant squared x minus 1. So I'm just using sort of a modified form of that identity. I'm saying, okay, I've got secant squared x minus 1 times a secant squared x times a secant x tangent x dx. And then if I put in all my u substitutions, I've got u squared minus 1. I've got u squared, and I've got du. So the idea is to get this all down to some sort of polynomial that's relatively simple to integrate. So I'm integrating u to the 4th minus u squared du to get u to the 5th over 5 minus u cubed over 3 plus c. And finally, everything gets written in terms of secants. Secant to the 5th of x over 5 minus secant cubed x over 3 plus c. So you can see these guys can get a little bit messy, but they're all doable. We just have to kind of crunch through them and stick with them until we get to the right answer. You guys are being quiet. I know that's a lot to absorb. Thoughts other than things are getting real?
It'll probably just take some time to get like the hang of it, but it's
Yeah, and I think you need
doable.
to probably go out and try some on your own too.
And this is all part of chapter 3.1, whatever we're in.
Yeah, actually, so 3.1, the first section was integration by parts, and then these trig integrals are all in 3.2.
Okay, so this chapter doesn't split off like as chapter like last one, like 2A
Oh
and
no,
2B.
no, it does split off. So it is going to be in two parts in terms of the test. The first 4 sections of the chapter from if you went to the OpenStax book, are part A or whatever I call part 1, and then the last 3 or 4 sections are part 2.
Oh, okay.
I can't remember how many there are altogether. Let me think. Okay, yeah, it's 3. So there are the first 4 sections. So integration by parts, and then these trig integrals. And then next time we'll look at what we call trig substitution, and then partial fractions. So we have four methods, really. Those are kind of the 4 big methods, and those will be on the first test from chapter 3. And then the second half of it will be some other strategies. Those include using tables and using computers. So we'll hit a lot of Mathematica on that, and we'll hit using your calculator on that as well. And then numerical integration methods. So this is for when we can't come up with a formula and we have to use an approximation. So a lot of functions just don't have a formula when you go to integrate them. There isn't a nice formula that you can get. And then something we call improper integrals, which just means that something's wrong with the limits of integration. Either they're infinite or they cause your function to be undefined. But you can sometimes still calculate the integrals. So that'll be the last piece of that.
Okay.
So yeah, it does split up into 2 pieces. And then you'll have the midterm over everything so far. So up through that end of chapter 3, and essentially the first 4 ALTA tests will have a midterm that will be written. So, and on the midterm, I will just upload it. You guys will do it, and then you'll upload your test.
About when do you think that'll be? When will that be
Well,
due?
tentatively, I had this wrong in the original, somewhere around, I think I had like October 21st to 28th, somewhere in that range,
Okay.
toward the end of October, mid to late October. And you'll have a few days to do that, so you won't have to do it all at once.
Okay, sounds good. Thank you.
You're welcome. Okay. So everybody's seeming a little bit drained today. Do you guys just want to go off and work and get things done and see what questions you have for me on Monday? Oh, yes, please. I don't like partial fractions, Merrick said. Okay, well, Merrick, I can't remember. Do you have a calculator? Do you have a Inspire calculator? No, but did you download Mathematica? Okay, so I'm going to show you how to do the algebra partial fraction stuff in Mathematica so that you can check it and make sure you're getting it all right. And I'm not going to make you do the super grungy problems by hand because I'm not really about that. So as long as you have one of those technology pieces where you can get the partial fraction breakdown for the nastier problems, you can do those, and then you can just do the integration by hand. And then they won't be too bad. We're not going to dwell too much on the algebra in here because you can always go back and figure out that you can always go back and use technology for the algebra piece. All right. So I think, okay, Aaron C., I thought I did that. Oh, you know what? I think I did the first test and I didn't do the second test. Is it from the first test or the second one, Aaron C., that I need to look at still? Second one. Okay. Thank you for the friendly reminder. That was nice and gentle too. All right. In fact, I will go do that right now if you guys want to go off and work on whatever, or just have another cup of coffee or a Diet Coke. And then I will see you all next Monday. And next Wednesday, we might not meet. I might do a couple little recordings of some example problems for you because I'm going to be attending a conference. It's virtual, but I think they will probably have sessions during our class time. So we likely won't meet next Wednesday, but I'll upload some recordings and they'll be shorter because I'll likely do like 1 or 2 problems, and then that'll be an upload, and then I'll do 1 or 2 more of some examples for what we're doing that day.
Sounds good. Thank you.
Okay, you're welcome, and have a good weekend, everyone.
You too. Bye.
Bye-bye.